Okay, I figured we would quickly go through the exam just to make it easier in the long run. So for question 1, this is going to be for version A, but version B, C, D, it's all the same questions. They're just in different orders, and the answers are in different orders. So just find the analogous one you need in version A to solve it. So hopefully you selected this. It was worth points. There were about 40 people who didn't put their exam version down, so yeah, I kind of needed it. Okay, report the following arithmetic result to the correct number of sig figs. So remember order of operations, so we can start with either of these two. We'll start with the one on the left. It's division. 1, 2, 3, 4, 5 sig figs on top. 1, 2, 3, 4, 5, 6 sig figs on the bottom, which means whatever this number is, we'll have 5 sig figs. So since we're summing them all together in the end, it's going to be 14.4285543, and my error will be right there. Then we have this. We're going to do math up top because it's in these parentheses, and that will be 4.5, which is 2 sig figs divided by 1, 2, 3, 4, 5, 6 sig figs. So this number altogether is here. So 17.533947. 2 sig figs divided by 6, which means our sig figs are there. And lastly, the log of 532.4, which is 2.726238. And we have 4 numbers, so 1, 2, 3 are significant figures there. When we add them all together, we get this. And our largest error is in the ones column. So it has to be in the ones column, so it has to round. So our answer is A, 35. Report the following arithmetic, correct number of sig figs. So once again here we have some multiplication, then we're doing some addition, or subtraction. So here we have 3 sig figs times 5 times 7. So this has 3 sig figs. So all of this together has 3 sig figs, which you'll put it right there, 1080.00014. Plus, so remember that had 3 sig figs, plus 2323.274, since it's a number itself, it's right there. And 3,245, that's in the ones place. All that together, well, this is plus, this is minus, it goes to being this answer, and the largest error is in the tens place, which is right there. So this will round up, giving us our answer of 160. For the ruler on the below, wow, that's good language on my part. How many significant figures should be reported for the measurement of the bar below it? Okay, so we want to measure this bar. How many sig figs will this bar be? Okay, well, let's just do the math. This is going to be 93.9, and then maybe a 1, it looks like. And then, I'm sorry, it's 92. 92.91, and then over here is 92. I'd say 0.9. So we'll do the math. 9 goes to 8. 11, that's 2. So 0.82. 0.82 will have 2 sig figs. So even if this was increased by, if you said 93 or 94, or that was down by whatever, it'll still be 0.8081828384. So it'll always be 2 sig figs. A good way to notice that is the primary 2 leading sig figs here will disappear because they're both the same. Okay, 5. Select all the definitions of select the definition of significant figures. So all certain digits and no uncertain digits. Well, that is incorrect. all the certain digits plus the first uncertain digit. That is correct. All certain digits that follow the decimal point. Yeah, not true. It could be further out to the left. You have no idea. And is perfectly fine. All the certain digits that precede the decimal point. That's awful. I made that up. All the certain digits plus 2 uncertain digits. I made that up too, of course. So yeah, you'd probably recognize that one right off the bat anyway. So all good. So report the following arithmetic with the correct number of sig figs. So the way to solve this, of course, is to look at what the answer is and put everything in that power. So 3.9256, right, times 10 to the 12th. I may just quit writing that though. So 9, right? So if this is 6.3 and it's to the 9th power, the decimal place would move here for the 10th, 11th, and 12th. So 0.0063 times 10 to the 12th. Okay, this is 7.27. I'm just drawing the first ones. So it's a 10th power, 11th power, 12th power. So 0.0727683 times 10 to the 12th. 8, and of course that will slide over 1 for the 10th, so 0.837 times 10 to the 12th. And so when we add all those together, where is our largest error? It's in that third decimal place in, which will be here, and then that will round up, giving us the answer is E. A student calculates the average and standard deviation for the pressure of an unknown gas as this number. Dial for the gas meter shown on the right. How should the result be presented? So, once again, rule 1, what does my error have? Okay, well, my error here starts, does begin with a 1 or 2? Nope, so I can only keep 0.004. Rule 2, I must match that, 3.63. And rule 4 doesn't make sense. Well, let's see. What can this show for decimal places? So I'm going to just pick a random point. Boop. Okay, so there's my random point. Oh. Nope, go back. Thank you. So what is that point? That's 2. And then next to that is 0.1, 0.2, 0.3. And then my first thing I have to guess at is in between. I'm going to guess 5. Okay, so, oops, I didn't match this one correctly. 2.9. So that means in this system, the best my gas meter can do is to that decimal place. So this is a smaller error than that. So in reality, I have to match what my gauge says and then make everything match. 3.63. So this would be the answer, and here for 7, it is D. Okay, good. Student calculates the average and standard pH of an unknown acid as this number. The pH meter shows 2 decimal places. How should the result be presented? Okay, rule 1, does it begin with a 2? Yes, it does. So I have to keep 2. So minus 0.298. This will round it up, because that, and then it becomes 0.3, right? And once we have 3, we have to keep 1, so it stays as 1. Yeah, so this is a lost herring, right? And so then it just has to match 9.7. Okay, so for rule 2, so rule 1, rule 2, rule 3. What are we doing here? It's got to be 0.01 is their instrument. 0.3 is much larger than the instrument, so it is E. Okay, number 9. A student calculates the average and standard deviation as a point of an unknown acid as such. The pH meter shows 3 decimal places. How should it be represented? Rule 1, 0.005, right? Because it doesn't begin with a 1 or 0. Rule 2, 12.523. Rule 3, our meter best is 0.001. What's bigger? Well, the 0.005 is bigger. So there's 2 0.005s here. One has the correct number matching, the other one does not. A. Student measures the pH of an unknown acid 3 times and obtains the average of this and a standard deviation of 0. Okay, so the pH meter is shown below. How do result be represented? Well, as soon as you go to rule 1, you realize that, oh my god, it's really 0. So there's something wrong, right? You probably had 3 exact measurements. You take the average, and then the standard deviation is this. Actually, technically, if you think about it, you could never actually get that number. But not the point. Not the point. The pH meter is this, so our pH meter error is going to be 0.1. So our answer is plus or minus 1, right? So we're going to just use this, 9.7 plus or minus 0.1. Okay, moving on. The pKa of an acid. Okay, the pKa of an acid is reported as this. pKa logarithm. Okay. The corresponding value of Ka is shown on your calculator. So this is the inverse of the logarithm. Okay. Report the concentration with the correct number of sig figs. So if this is a logarithm, only to the right of the decimal place matters. So I have 3 sig figs. So that means I need to report this new number, the anti-log, to 3 sig figs. So 3.3 would be 6, but we have to round it. 7 is the correct number of sig figs. Okay. Number 12. An acid has a Ka value of 7.28 blah 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 times 10 to the minus 9. The corresponding value for pK shown on your calculator is this. So remember, this is a logarithm and this is normal. Okay? Report the pK with the correct number of sig figs. So this one has 1, 2, 3, 4, 5, 6 sig figs, which means my answer has to have 6 sig figs. So it has to have the 12, which is not sig figs, then 1, 2, 3, 4, 5, 6. And of course that's going to have to be rounded. Sig figs. Boom. Awesome. A student measures the mass of a precipitate for 6 trials using the balance shown below and calculates the average and the sample standard deviation as such. How should the student report the result? Rule 1. Right, 0.0005, nope, 6, because it has to round up. Awesome. So we have 4 decimal places, 8.3205, because it rounds up. So there's rule 2. Rule 3, okay, this is my device, so 1, 2, 3, 4, so 0.0000. So what's bigger, a 6 or a 1? Of course, the 6 is bigger. So B is our answer. Okay, 14. You measured the mass of 3 alquats of lithium fluoride using a balance that has 4 decimal places and get the following masses. Okay, you calculate the number of moles of each aliquot using a calculator. The calculation for the first aliquot is as follows. The average number of moles, the sample standard deviation for the 3 aliquots show up on your calculator as such. How should this report be resulted? Step 1. Okay. What is rule 1? So plus or minus 0.0003. Okay. Rule 2 must match. 0.281 should be 7, but rounds to 8. And rule 3, where's my instrument error? If you go, oh, it's a 1 or whatever, that's really not the way you should do this, because the balance, right? You really need to look and say the balance has an error here, but my other value has an error in the 3rd decimal place. So in reality, my error from everything is in the 3rd decimal place right there because of sig figs, right? Because 5 sig figs and 3 sig figs. 5 sig figs times 3 sig figs is only 3 sig figs. So my error in this system is plus or minus 0.1 based on the instrument, okay? Really what's driving it is you don't have a good conversion, right, to grams per mole. So in reality, with rule 3, it should be plus or minus 0.001, and then this goes to 0.282. Okay, so 282. Awesome. You measure the mass of 3 alcohols using this balance, 4 decimal places. You calculate everything very much the same as above. Here you have a new average and standard deviation. Rule 1, plus or minus 0.00, rounded up to 3, so keep 1. Then 0.282 to match. Rule 3, where's my error? 5 sig figs times 3 puts it in the 3rd decimal place, so 0.001. So if 0.001 is my error and my standard deviation is 0.003, standard deviation is bigger, so the number I have then stays as such. Okay. A student measures the mass of precipitate using 3 different balances that show 3, 4, 5 decimal places and record the following values, right? The average collected is then done from this, what are the number of sig figs you report? Well, if you remember when you do your addition in this, what really sets your value is going to be the one with the largest number, right? So you have 31.67204, you have 31.3529, you have 31.737, right? So when you add these together, you are stuck, right? Everything you're doing is stuck in this decimal place because of this one scale that only reads to 3 decimal places. So you are limited by the instrument in this scale. Once you take the average, sure, you want to say, oh look, I have 5, this many sig figs divided by infinite sig figs, so once again, I would have 5 sig figs. But really what's going on here, even though it shows the same spot, is the limit is really that 3rd decimal place. Right? Quite often, I keep telling you can't use grams because you're, that decimal place in grams because, you're doing moles. But this time we're doing grams to grams, right? So, yeah, it's that 3rd decimal place that sets the difference. Okay, you buy 2 identical thermometers and use them to measure the same solution at the same time. Okay, the temperature is measured 4 times on each, right? And you get some average and standard deviation. Okay, select one. One can neither comment on the accuracy nor the precision. Well, we do have some information here, but let's see what else is in here before we go to that A. Thermometer B is less accurate but more precise. Okay. The problem is this right here. Thermometer B is less accurate. Right, we have 2 different temperatures, right? We'll call the one on the left A and B. This is 79. This is 74.4. Accuracy is how close you are to the target. We really don't know the temperature of this water at all. So there is no accuracy, right? We can't say anything about the accuracy because we actually don't know the real temperature, right? Having 2 temperatures that are different really makes it suspect. So, no. Thermometer B is more accurate but less precise. Once again, we can't talk about accuracy. Just can't do it. Right? Thermometer B is more accurate, but one cannot percent on the precision. Once again, we've talked about accuracy. We don't know what the target value is, so we can't see how far we are away from that target value. Lastly, thermometer B is more precise, but one cannot comment on the accuracy. Okay, we can talk about precision though, right? Precision for A is simply going to be 3 divided by 79, and the precision for B is going to be 0.2 divided by 74.4, right? We don't have to do the math to see which one of those is going to be smaller, right? This will be smaller, there'll be higher precision, right? that is a systematic error. It does not reflect on the precision of the instrument at all, right? So with this ratio, we can say that yes, thermometer B is actually going to be more precise, and we can't comment on the accuracy. So E is 100% correct. So in reality, we can comment on the precision. So A is not right. So for 17, E is the answer. This is a conceptual question. It's, it takes critical thought. Okay. Select two false statements. Okay. Repetition of measurements will reveal random error. Okay. That's absolutely true, right? That's true. Random error shifts the results in only one direction. No, actually it does a Gaussian distribution. So we know B is false. You should, right? Random errors, are always both directions. Systematic errors are only in one direction. Random errors always have a Gaussian distribution. Yes, they do. That's true. Random errors, in theory, can be identified. Okay, so if I have you just take something off the scale and put it back on the scale over and over and over, you're going to get different measurements. You'll never be able to figure out where that is. Now with a systematic error, yeah, you can identify it. Random errors are not really identifiable, right? Miscalibration of an instrument always results in a systematic error. That is true. So the answers to these two are for this one is B and D are the two false statements. 19. After 34 trials, the average mass delivered from a pipette is 10 grams with a standard deviation of 1 gram. Okay. If you perform a 35th trial, what is the probability the mass will be between 0 and 8 grams? Select one. Okay. Let's do it. Well, we have a standard Gaussian curve. Our average, right, is 10. And we want to know between 0 is way over here, and 8. So here we have 9. Here we have 8, right? Our standard deviation is 1. So 8 is 2 standard deviations away, right? So 2 sigma. So I'm just going to erase 9 for now, right? And this is 2 S or 2, well, it's actually S because it's a trial. Okay. So we know for 1 S, 68% is in between. For 2S, it's 95, and for 3S, it's 99.7. So between 8 and 12, right, that's 95% of the area under the curve, which means these two areas on the side have a total combined of 5%, where 2.5% is here and 2.5% is there, right? So in order to get from 0 to 8, there's a 2.5% probability that it will fall within that area. Okay, moving on. Select a true statement about RSD. Select one. Okay. The sample RSD approaches the population RSD when the sample average approaches the population average. Right? This is totally false, right? Remember in class when I talked about, all the 5'8" people stand up. You remember our averages were the same, right? So the average height of the class, the average population in the United States, and then just the 5'8" people in the class had the identical average, but we had different standard deviations, right? In reality, we only talked about two things. We talked about S or sigma, S approaching sigma as N approaches big N, and we talked about X bar approaching mu as N approaches big N, right? So, yeah, interesting. Let's just skip B for a second and move on to C. RSD provides information about accuracy of the measurement. No, RSD provides information on the precision not the accuracy, right? That would be percent error. Okay, now remember, the sample RSD approaches the population RSD when the sample size approaches the population size. This is true, and we're going to talk about why it's true. You're going to say, you didn't tell me about that in class, and yeah, I didn't. But remember, RSD is simply S over X bar. And we know that this approaches sigma, and we know that this approaches mu. So yes, as n approaches big N, we do know that the sample RSD approaches the population RSD, right? So you had to reach back and put together two different things. One, that you know this, and two, that you knew this, this relationship. Once you have those two in your mind, you can clearly see B is true. More than one is true, no, and none are true is not correct. So B is the correct answer to number 20. Okay, 21. How should you report an average and its corresponding standard deviation? Select one. The average should be reported at the same decimal place as the standard deviation. Absolutely true, right? If you have plus or minus 0.003, then your answer has to be 1.234. Perfect. The average and standard deviation should have the same number of significant figures. Well, your standard deviation will either have 1 or 2, depending on if it begins with a 1 or 2 or not. So this is absolutely false. Not good. The average and standard deviation should have the same number of significant figures and the same number of decimal places. Well, that just compounds upon B. That's even worse. The standard deviation should report with one more decimal place than the average. I made that up. Sounds pretty good, though. Right? It has no room in any of our three rules. And, of course, none of the above is not true either, because we've already determined that the correct one is A. Select two false statements. The percent RSD provides information on the relative accuracy of one system to another system. Now, once again, RSD does precision, right? And percent error does accuracy. So that is totally false. Random error is revealed with repetition of the measurements. Yes, the more measurements you take, the more you know about your system. So this is true. Pardon me. Random errors reflect statistical... Random errors reflect statistical fluctuations associated with the measurement. Correct. Those statistical fluctuations are in the form of the Gaussian and then go both ways. Great. Repetition of measurements will reveal the size of the random error. Yeah. As you know more about the random error, right, you know more about its size. Specifically, S approaches sigma, right, as N approaches capital N. So absolutely true. Random errors can be compared by calculating percent error. Once again, that's false for the same reason. A is false, right? Random errors are RSD. So basically, 22 is the same question twice. 23. You have a balance that's not calibrated and reads the masses are too low. You use this balance to measure the mass of a precipitate multiple times. What happens if you increase the number of mass readings with this miscalibrated balance? The population mean approaches the true value of the mass of the precipitate. Okay. The mean, right, the average weight will never approach the true value because it's miscalibrated, right? So if the true mass of someone is 100 pounds and your balance is reading them 80, you'll get closer to, 80, 80, 80 every time. So that just it's not going to work, right? Because you're miscalibrated. Specifically, it talks about accuracy. So you'll never get the true value, which is, accuracy. The sample mean approaches the true value of the mass of the precipitate. Once again, the sample value, the sample mean, approaches the true value of the no, once again, it will never approach the true value. You'll never get the correct thing, right? You'll never get the correct answer as long as it's miscalibrated. The sample standard deviation becomes large and approaches infinity. I don't even know what that means. I made that up. Sounds pretty good, but I needed something else to put in there, so yeah. The sample standard deviation becomes small and approaches zero. Totally made that one up to balance off the one above it, because, wow, that would look good. And the sample standard deviation approaches the population standard deviation, yes. So even though your accuracy, this is what's really cool, your accuracy tanks, your standard deviation stays the same because the error in the instrument is the same, it's just miscalibrated. So it doesn't give you the correct answer, but it still gives you the same area around that number. You want to prove this to yourself. You can do that with take some measurements, 1, 2, and 3, and it really should be 2, 3, and 4, right? Together, this is going to be 6 divided by 3, so your average will be 2, and then this one your average will be 3. So this would be the miscalibrated value, and this is the correct value. But notice that if you would do the standard deviation, where 1 minus 2 squared is 1, right? 2 minus 0. 3 minus 2 squared is 1. That these numbers here versus that number give you the exact standard deviation numbers, right? So 1, 0, 1, 1, 0, 1. And then so the standard deviations will be the same. So you can always prove it with just a couple numbers on the margin of the page. What is the correct reading for the burette on the right hand side? Well, 3,000 is a definite certain number. Then there's 100, 200, 300, 400, 500, 600. I'll call that 700. And then the first one, so that's then the first one that we have to guess on is going to be in this decimal place. I'd actually probably say it was 0 and then 0 to set the thing. So basically we need 3 sig figs. This one has 5. This one has 2. This one has 3. This one has 6. And this one, because the decimal place, has 4. So only one of these could be a correct reading from the system. I wasn't really looking for what the value is, right? And because B really only has 2 sig figs, it is absolutely not correct. There you would have to denote this as being correct, or 3.70 times 10 to the 3rd power, right? So only C could be correct because it's the only one that has the correct number of sig figs. Number 25, I put this one in here. Once again, the pH one here is really me doing a stopgap. I want to know how well you are learning, and I want information before this lab report is due. I know it's not sig figs, but it's also not going to be part of your grade for the midterm. So this question doesn't count on the midterm, but what this does is it gives me feedback real time on how you are performing. I know a lot of you are watching it on podcast, and a lot of you don't like answering questions in class. I get it, but I still want some feedback, and so the only way for me to get feedback is to surreptitiously, sneakily put it on your exam, and then I can get feedback on how you're tracking in this experiment. Okay, so we calculate the pH of equivalence point, weak KHB titrated with strong base, yay. What information was not needed to select the appropriate indicator? The pH at which the indicator dye undergoes a color change, right? I want to make you understand that dye undergoes a color change at a specific pH, right? That the weak acid has a pKa, right? And that it won't be the correct, it won't have its equivalence point at pH 7, right? You do need the concentration of the sodium hydroxide, right? Otherwise you can't, that's why the whole point we're doing for this. right? Because we have to figure that out in order to get the good system. You also need the initial pH, right? Because this was in the ice table. We did this as a calculation. The initial pH of the weak acid before it was titrated, we calculated it, but we didn't use that in the calculation to determine the pKi, the indicator. And the initial concentration of the weak acid, you definitely need that in order to do the ice table. So the answer is D. Once again, not used for points on midterm, but really I want to see how well the class is tracking to see if we need to augment. Okay, well, hopefully this answers questions and helps you understand sig figs a little bit better. We're just about done with the corner, so keep up all the great work.